In Chapter 4, we're going to be comparing two network architecture models, namely the OSI model and the TCP/IP model. First, protocols. So, in terms of, you can break it down into syntax, semantics, and timing. So, syntax concerns the format of the data blocks, whereas semantics includes all the control information for coordination and error handling, whereas timing includes speed matching and sequencing. So these are some key factors when you talk about a protocol. Next, we need to understand what agents are involved in communication, namely the applications. So these are the exchanges that take place between computers. Also, email could be an application, for instance. Computers are devices that are essentially connected to a network. A lot of time you call this the client. And then the network itself, which transfers data to and from various clients or computers. All right, so in this little concept diagram, we have host A and host B, and then you have various applications that can run on host A, and then this rests on this TCP and IP network protocol stack, and it goes, this is network access under protocol 1, and then this goes to the physical layer, which is kind of like the front end of a protocol stack. Within this layer actually interfaces with the real world and sends over the air or wires or whatever your network configuration is. So then host B, very similar concept. You have applications running at the application layer of host B, and this interfaces with a protocol stack, and the physical layer interfaces with other networks. And then this would be like a router, for instance, and again, physical layer is what interfaces with other networks and or the outside world, essentially. So the TCP/IP network architecture stack consists of 5 layers. Its bottommost layer, is referred to as the physical layer. So this is what's going to interface with other networks, and then you kind of then you have the network access layer, the internet layer, you have the host of transport, then you have the application layer. So it looks like the application is running on my computer right now called Gmail. I actually have voice over IP that's basically trying to accept a call on my behalf right now. So that's the noise you hear in the background. So here you have protocol data units, also called PDUs, in TCP/IP architecture. So you can see up at the top you have user data. That's an application byte stream, and then you attach TCP headers to that, and that becomes a TCP segment. Then you attach IP, or an Internet Protocol header, and that becomes your IP datagram or datagram. And then you attach a network header, and that's called a network level packet. So you can see by attaching these various headers, you kind of append them to the user data, and it basically allows for the data to flow across the different layers of the protocol stack. So the physical layer, just to get a little deeper into it, covers the actual physical interface between a data transmission device and a transmission medium or network. The physical layer will specify which characteristics of the transmission medium you're focusing on, and then the actual nature of the signals and the data rate that the data will be transmitted at. So whether it's 5 megabits per second, 10 megabits per second, or 50 megabits per second, and then other related matters. So the access layer of the TCP/IP network architecture is concerned with the exchange of data between an end system and the network to which it's attached. The software used will depend on the type of network. So whether you're talking about a circuit switching network, which is covered in Chapter 3, or a packet switching network. So example of a packet switching network would be X.25, and then local area networks would use Ethernet, and there are many other types of software and hardware associated with the access layer. Then you have the internet layer. So this uses, you've all heard of IP or Internet Protocol, and this takes place at the internet layer. So the internet layer also provides routing functions to allow data to traverse multiple interconnected networks, and it's implemented in end systems and routers. Then you have the transport layer, also called the host-to-host layer of the TCP/IP architecture, and this commonly uses transmission control protocol, so that's what TCP stands for, and it provides reliability during data exchange. So just think, we often talk about the integrity of data, so it just ensures that the data that's being transmitted between various networks is transmitted reliably. So completeness and that the order is correct, so it's concerned with sequencing there. And the transport layer, just think transporting data from point A to point B, transport layer or host-to-host layer. Finally, you have the application layer. So this is what interfaces with the user. So it's the logic. This logic supports user applications, whether it be email or other type of application. I mean, just think apps, right? App is short for application. So really anything you can think of where you have user input or user interfaces is considered an application. So it could be Word or a Microsoft Word or some sort of text editor, or it could be IDE, like an integrated development environment for coding or whatever application is running. So it uses separate modules that are peculiar to each different type of application. Some common applications you might utilize in the TCP/IP framework is the Simple Mail Transfer Protocol, so the SMTP, and it provides a basic electronic mail facility. You may have heard of FTP. It was used very commonly used in the early days of the internet, file transfer protocol, which allows for files to be sent from one system to another. The one you've probably heard of and used the most throughout your time surfing the internet would be the Hypertext Transfer Protocol, HTTP. A lot of websites start with either HTTP or HTTPS if it's the secure version, and it just transfers information over the World Wide Web. Now we come to the OSI model, which is actually a different model to focus on with regard to network architecture. So it's different than TCP/IP, and we'll compare them side by side in a bit. But this consists of 7 layers. So you have the application layer, similar to the TCP/IP, but then you have the presentation layer, the session layer, the transport layer, which again similar, the network layer, data link layer, and the physical layer. So you can see there are certain layers that are common to the TCP/IP, but they're defined slightly differently, which makes it a little bit confusing. But we'll make sure we define them side by side so that it's clear. So this goes into a little bit more detail, showing the roles of the various layers in the OSI model, and we're going to dive right down deep into these right now. So the application layer provides access to the OSI environment for users. Very similar role played here between the OSI model and the TCP/IP model. So just think application layer is just what's interfacing with the user. And it provides distributed information services. The presentation layer provides independence to the application processes from differences in data representation or syntax. So the session layer provides the control structure for communication between applications, and it also establishes, manages, and terminates connections or sessions between cooperating applications. So That's what the session layer accomplishes in the OSI model. Then you come to the transport layer. When you're thinking transport, you're thinking the transfer of data between endpoints, okay? And it provides end-to-end error recovery and flow control. So transport layer, the OSI model, very similar to the TCP/IP model in that you're thinking the transfer of data between hosts or endpoints. Then you come to the network layer, which provides the upper layers with independence from the data transmission and switching technologies used to connect the systems. And it's responsible for establishing, maintaining, and terminating connections. So that's the network layer of the OSI model. Then you come to the data link layer, which provides for the reliable transfer of information across the physical link. And it sends blocks or frames with the necessary synchronization, error control, and flow control. So that's the data link layer of the OSI model. Finally, you come to the physical layer of the OSI model, very similar to TCP/IP in this case, because you're concerned with the transmission of the unstructured bit stream over the physical medium. This is what interfaces with the outside world. It deals with accessing the physical medium in terms of mechanical characteristics, electrical, functional, and procedural characteristics as well. So TCP/IP has somewhat taken over in terms of the dominant architecture that's kind of accepted by the community. And a lot of this has to do with the fact that it matured faster than comparable OSI protocols. So when the need for interoperability across networks was recognized, TCP/IP was the only ticket. It was available and ready to go. The OSI model is recognized by the community as being unnecessarily complex, and even though it provides a nice breakdown of kind of all the layers and it goes into great detail as to what they comprise, it's looked at as being inefficient because it uses 7 layers to accomplish what TCP/IP accomplishes in 5 layers. So just realize that TCP/IP is the recognized dominant architecture. So here's that side-by-side comparison I was promising. So you can see application layer of the OSI model plus the presentation layer and part of the session layer comprises is comparable to the application layer on the TCP/IP side. Transport, it's not a perfect one-to-one there, but part of the session and part of the transport of OSI comprises the equivalent transport layer of the TCP/IP. And then the network layer of OSI is basically comprised by the internet layer plus some of the network access layer of TCP/IP. And then you can see that the only one-to-one match there is the physical layer between the two models. So that's important to know. So here you have a TCP/IP example of a configuration of a network. So you have upper left corner, you have a server. Let's just say you have an ATM network. You have to have a router to route the packets appropriately, and then you could have a IEEE 802.11 local area network. So you're thinking Wi-Fi there, and then some sort of client or workstation. And here you have the physical layer that's basically communicating between the various entities in the network. Okay, so in this case, the operation of TCP/IP, so this is the action at the sender. So it prepares the data. The application protocol prepares a block of data for transmission. It could be an email message, and then essentially using common syntax, if necessary, the data is converted to a form expected by the destination, and then it segments the data, and then it duplicates segments if necessary. A copy is made of each TCP/IP segment in case the loss or damage of a segment necessitates retransmission. And then, of course, an acknowledgement will be sent back from the other TCP entity, and a segment is erased. And then there may need to be a fragmenting of the segments in which the IP may break a TCP segment into a number of datagrams to meet size requirements of the intervening networks. And then framing, which is a link layer header, is added to each IP datagram to form a frame. So this is essentially how a TCP IP action at the center would operate. Then you have the action of the router. So you're going to have to get into it here a little bit. So the router routes the packet appropriately. So the Internet Protocol examines the IP header and makes a routing decision. It determines which outgoing link is to be used and then passes the datagram back to the link layer for transmission on that link. So then, okay, so that's step 10 actually. Take a step back, it's kind of going like this here. So first, let's take a step back. The packets arrive at the router. The incoming signal is received over the transmission medium and interpreted as a cell of bits. Then you essentially process that packet. The link layer removes the frame header and processes it. The header error control is used for error detection, and the connection number identifies the source. Then you route the packet accordingly, and then you form packet data units, and an LLC header is added to each IP datagram, and then the header contains sequence number and address information, and then you perform framing. So media access controller MAC header and trailer is added to each LLC PDU, forming a MAC frame, and the header contains address information and the trailer contains a frame check sequence. And then finally there's transmission, so each frame is transmitted over the medium as a sequence of bits. So then you have the action at the receiver. So starting down here, you kind of undo everything that you performed at the transmitter. So it arrives at the destination, the incoming signal is received over the transmission medium and interpreted as a frame of bits. You process the frame, so the MAC layer removes the header and trailer and processes them. The frame check sequence is used for error detection. Then you process the packets and remove the header and essentially process it. The sequence number is used for flow and error control. Then you process the IP datagram. The IP removes the header and the frame check sequence and other control information are processed. Get into IP call. Process the TCP segment, reassemble the user data, and deliver the data. So the elements of standardization within the OSI framework. So there's protocol specification, the format of the protocol data units or PDUs exchanged, the semantics of the fields, and the allowable sequence of the the protocol data units. Then there's the service definition, functional description that defines what services are provided, but not how the services are to be provided. And then there's addressing. So the entities are referenced by means of a service access point or a SAP. What about internetworking terminology? So there's the communications network, is a facility that provides data transfer service among devices attached to a network. There's the internet, everybody's heard of that, collection of communication networks interconnected by bridges and routers. Then there's intranet, which is an internet used locally by an organization for internal purposes, and it provides key internet applications, intranets can exist as an isolated self-contained internet if desired. More internetworking terms include end system, or ES, is a device used to support end user applications or services. Intermediate system is a device used to connect two networks. A bridge is an intermediate system to connect two local area networks or LANs that use similar LAN protocols. And a router is an intermediate system used to connect two networks that may or may not be similar, so they may be heterogeneous in nature. Functions of a router, we alluded to this earlier, but it provides a link between networks. It provides for the routing and delivery of data between processes on end systems attached to different networks, and it provides these functions in such a way as to not require modifications to the networking architecture of any of the attached subnetworks. There are many network differences that routers must accommodate, including addressing schemes, because there are different schemes for assigning addresses between different networks. Also maximizing packet sizes, so different maximum packet sizes require segmentation. Different interfaces, there's going to be different hardware and software interfaces associated with different networks, and also reliability. The networks may provide unreliable service in certain cases.